Okay, so we had a specific set of instructions that we were going to do. That video will be available as well so that we can actually see the instructions. But, okay, what were the instructions specifically on that one?
3 seconds accelerating, 2 seconds stop, 3 seconds stop.
What direction?
Direction.
So 3 seconds this way, and then what?
2 seconds stop.
2 seconds of stopping. Okay, and then
3 seconds stop.
3 seconds to the right. Okay, so all in total, we spent 6, 7, 8 seconds doing something, right? Okay, and part of it we were accelerating, part of it we were stopped, and the other part we had 3 seconds of to the right. So left is negative, right is positive. Are we okay with that? Okay, so when we make our graph, and since I just completely ignored the squares anyway, I'm just going to make a displacement versus time graph. I think this is easier to see. So if I do displacement versus time, and we can just be approximate. So there's 3 seconds is an important place. So I'm going to put 3 seconds here. 2 seconds after that, which would be 5 seconds. And 3 more seconds, which would be 8, right? So we got 3, 5, and 8. Okay, now displacement versus time. We have acceleration. So what is that going to look like? Curve. And about how far did we go? How many meter sticks? Let's just approximate. We don't have to be it exact. 4? Oh, yeah. You started right here, right? Start right here. Okay, 1, 2, 3, 4. I think about 4. Yeah, I think about 4. Good enough. So we went -4 meters. So I'm going to put -4 down here because I think that's about as far as we go. That means up on the top would be +4 meters. For a sense of scale, that's not completely unrealistic. And at 3 seconds, we ended up about right here. Now, we're going to draw a line that goes down like this, correct? No. What's wrong with that? It needs to be curvy. What kind of curvy? There's lots of curvy. There's this curvy. There's that curvy. There's this curvy. Which one? The last one? Okay. And that actually makes a lot. Oh, crap. I cannot actually reach the dot because I'm not very good at this. Okay, how about that? Because it starts off you're not moving as fast, and as you keep going the slope gets steeper. That makes a lot of sense to me. So that kind of curve is the way to go, and you want to make sure that it looks like a parabola, because as you accelerate you're getting faster squared. Okay, you're covering more distance squared. Okay, then for acceleration is accelerated. You are very correct. 2 seconds we are stopped, so what do? Flat line, flat horizontal line. Okay, and then stop there. And then for 3 seconds, we go to the right. Where did we end up? We went back to 0. That means we're probably going to be going, well, it's 3 seconds. So I think we will have a higher velocity then. So for 8 seconds, we make it back to here. But the important thing is, since we were going at a constant speed, there wasn't really a speed up or a slow down. It goes to that straight line, straight diagonal line. If you look at the um, slope, the slope at the very beginning is really low, and the slope on the other side, so you start off over on this side with a higher velocity, but on the other side, the slope gets steeper as we go along. So even though you started with a lower velocity here, you ended up with a higher velocity on this side. From 5 to 8, you covered the same distance, but that was because you had the same speed constantly all the way through. Okay. What if we made a velocity time graph of this? So I'm going to over here just make a velocity time graph. And we know that the slope of a line is a velocity time graph's velocity, but we have a slight problem. That's a curve. So what are we going to do about this? Like, you can't take a slope of it. What are we going to do? Just like pretend? I don't understand. Just pretend. Just like, it's okay. We're just going to pretend that everything's fine. We cannot yet find the slope of this line. In order to find out what the slope of this is, we're going to have to use what we call kinematic equations, and I have not taught you guys that yet. So So according to us, we don't even really know how to handle that problem yet. So we're just going to be like, whatever. Okay, so what we're going to do is we know that the slope is going to be negative, right? And we know we're going to figure that out later. Yeah, so like we'll come back in the notes and we'll be like, hey, remember this thing? And then I'll show you guys how to do that. The main point right now is to worry about the graphs and not the equations. We'll worry about the equations later. That's going to be its own thing. So are we starting with a zero velocity? Did we start moving with a zero velocity? What did we start with? Well, but y'all don't agree. But did you start at zero? Okay, so we started at zero, and did we end up with a positive or a negative velocity whenever we started? Okay, and were we accelerating? So that means that since we were accelerating, there's going to be some kind of straight line there. Okay, but I don't know what the slope of that line is because I don't know how to figure out the slope of this line over here yet. Okay, all right, now what about 3 to 5? Am I covering any distance? So therefore, do I have any velocity? So there's going to be this like break, and it's going to go from 3 seconds to 5 seconds. There's going to be nothing there. It's going to like jump to zero. Okay, so there's this kind of break point right here where it goes like, hey, I have a velocity, 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 velocity. Nope, I'm zero. And then at that point, you just kind of stop. And then after that, do we have a positive velocity or a negative velocity? Okay, we have a positive velocity, and we're going to end. We can actually find this distance if we wanted to. So we can find this value. We're covering 4 meters in 3 seconds. So that would be 1.33 meters per second. So that's a positive value at least. So we can write here that this is positive 1.3 meters per second from this location. Once again, it's going to kind of jump right there. Okay, and that's what your velocity time graph would look like. You would have one period where you have a negative acceleration. From 3 seconds to 5 seconds, you would have zero acceleration. And from 5 seconds to 8 seconds, you would have zero acceleration. The flat line means zero. Okay, so you would have a zero acceleration. Make sense? Are we okay? Shall we do the next set of instructions? Do y'all want to? Here, let's do next. Who's next? Come on. Come on. We at least at bare minimum have to do the impossible one. Yeah, we at least have to do the impossible one. So try that one. Yeah, we at least have to do the impossible one. It's a good enough spot, yeah. Okay. Yep. 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 Okay. Now, that one was a little weird, but that's because the instructions were a little bit different from normal. So what did the instructions say to do? Okay, up 2 seconds, then to the right 3 seconds, and then down 2 seconds. Okay. Now, the problem with this one is if you try to do 2 dimensions with a motion graph, you're not going to get it doesn't work because whenever you deal with the motion graph and you do displacement versus time, you are only dealing with one direction of motion. So a displacement versus time graph can only handle positive and negative. It can't handle up and right and down because these are actually coordinates that have positives and negatives associated to them. So like if you're in the first quadrant, that's 2 positive numbers. I should probably write it like that. But if you're in the fourth quadrant, that would be positive x, negative y. So since you have 2 directions involved there, you cannot do that. So if you ever get one where you have directions that are in 2 dimensions, you literally can't do a displacement versus time graph. That would be impossible. So that one gets a frowny face. That's all you can really do there is just say no to it. Okay, so one direction and one direction only would be all you would need to do on that. Okay? Does anybody else want to try theirs? I'm not going to make you, but if you want to try yours, you're more than welcome to. We have enough examples that we can move on with our life. Going once, going twice, sold for 15 cents. Fair enough. That works for me. I just wanted to kind of give you guys a physical example of how this stuff works. So, where would you guys like to proceed from here? Do you have any questions on homework, or shall I move on to the next thing, or what's up for y'all? What went down yesterday is we talked a lot about the um, distance versus time graph, velocity versus time graph, and acceleration versus time graphs, and how to actually write those down. I do record all of the lectures, so you'll need to just go back and watch that video, and it's all there. Like it literally is all there, minus the people talking because a lot of the like I do a lot of noise cancellation, so it takes out most everybody talking, mainly for privacy reasons, um, to try to keep that as anonymous as possible. So when it comes to the homework, though, I haven't released any new homeworks yet, so it's been 1.2 and 1.3 have been it. The next one that comes out is 1.4. That's over kinematic graphs, which is not too terribly bad. Um, but I think the next thing is kinematic equations. So that thing that I told you guys that we don't know how to do yet, we're getting ready to know how to do it. So is that what y'all want to do, or if I have no questions on the homework, I'm just going to move on. Okay. If at any particular point in time you have questions on the homework, like you haven't done it yet, and you have questions on it, you can ask me. We'll answer them in class. Okay. Just as long as we don't like do the whole assignment, I think we'll probably be okay. Um, but if you had like one or two questions and you're like, yeah, I really need to do this, then that'll work. Okay. So let me just double check and make sure that the next one is actually kinematic equations, because if it's not, then I done goofed, and we'll move on to it. AP Physics. I don't want to accidentally get out of the way things go. Kinematic graphs. It is kinematic equations. Okay, fair enough. Here comes the fun part. There are kinematic equations, and um, the kinematic equations are used to find relationships between displacement, velocity, and acceleration, and time, dvat. Okay, distance, velocity, acceleration, and time. So there are several different kinematic equations. The AP Physics 1 formula sheet has three of them. There is a fourth kinematic equation that is really useful, but you can look that one up on Google if you want to. Since the AP Physics exam only lists those as the equation sheets that you have readily available to you, those are the only ones that I teach you, because if you try to rely on the other one and you don't have it memorized, then you're not going to remember it and it's not going to be there, and that's not going to be good for you. Okay. But anytime that you see in a kinematic equation D, that stands for displacement, V stands for velocity, A stands for acceleration, and T stands for time. And remember, whenever I was talking about if you were trying to find the velocity of an object, and that's displacement over time, this works if you have going over some constant distance over a time. And that constant distance over time would give you like an average velocity. And the same thing is true for the acceleration equals velocity over time. These assume that you have constant velocity or constant acceleration. Okay? So if you have some kind of constant acceleration or you have some kind of constant velocity, then these equations work out okay. But that's not necessarily always the case. So we need the kinematic equations to help us out in the times whenever situations get a little bit more complicated. So here's a couple more that deal with velocity, distance, and time and can actually help us solve for specific moments in time. Okay, and the equations go as follows. Vf equals Vi plus At. The F and the I stands for final and initial. So that would be like starting speed and ending speed. Okay, that's one of them. The other one is Vf squared equals Vi squared plus 2 times acceleration times displacement. Vf squared equals Vi squared plus 2Ad. And the last one is displacement equals VIT plus 1/2 acceleration times time squared. Okay? So if we had our situations set up and we just kind of analyze these equations a little bit, some of these equations have some of the variables and they ignore some of the other variables. So if we write our dvat in a little table, the first one, that Vf equals Vi plus At, that one has your velocity, your acceleration, and your time, but it doesn't have distance in it, or displacement, I should say, I'm sorry. And it literally just kind of leaves it out. There's only three of them. So the first equation, check, check, check. It has these three. It'll link velocity, acceleration, and time together. And honestly, this Vf equals Vi plus At is just a really kind of clever way to rewrite the top one up here. Okay, because the velocity, if you change your velocity, that would be like a delta V. So that's Vf minus Vi. So if you rewrite this equation down here and you solve it for acceleration, that would be Vf minus Vi equals At. And then acceleration would equal Vf minus Vi over T. Oh, that looks familiar. Oh, that's because it's that equation on the left side. Okay. Now, sometimes that works, sometimes that doesn't work. That is the simplest equation because it just has no squareds in it, and if you can get away with using that, I would always use that one if you can get away with it. But sometimes they don't give you things like time, for example. So if we look at the second equation, Vf squared equals Vi squared plus 2Ad, that's got velocity, that's got acceleration, and that's got distance, but time is left out. So if they give you a situation where you don't have the set time interval between those two things, you can still find the total displacement that traveled, but you have to do it using Vf squared equals Vi squared plus 2Ad. And that's how you would get it actually solving for uh, the velocity having no time. Okay? And the last one has displacement in it, and it has, let's see, we've got displacement. We have an initial velocity, and we have an acceleration and a time, but there is no VF. Okay, there's no final velocity in there. So the last one will give you information about the initial speed or the displacement that got traveled, but you don't necessarily have the final speed in it. The last one, the one on the bottom, is really, really useful for falling things. Okay, because if you think about it, whenever you take something and you like drop it, there's a lot of things that you can really easily measure at the very beginning. So, like for an example, if you're on a cliff and you take a rock, don't throw yourself off the cliff. If you take a rock and you drop the rock off the cliff, there's a couple of different things that you can measure. Okay, um, easy things that you can measure. First of all, what is the initial velocity whenever you take an object and you're just dropping it off of a cliff? Zero, right? So whenever you have an initial velocity of zero, you are starting off with no velocity right here. Okay. Can you measure the acceleration of an object that's falling? Okay, let's think about this. Can I measure the acceleration of something that's falling like this piece of tape? How do I do it? Oh, we know. Wait, what? Oh, it is the distance that we fell, and we can find that equation. But since we're on Earth, this value is the same thing no matter what. Okay? And that's true for every single thing. If I take this piece of Elmer's glue and I take this object that's tape and I drop them, they're going to hit the ground at the same time, right? True? Do what? Not necessarily. Why not? Okay, so, but in this case, the air resistance would be negligible between the two, right? Okay, so like if I drop both of these, they hit the ground at pretty much the same time. Okay, and if it was a feather, they would hit the ground at the same time if air resistance wasn't there. Okay, so if I take this, for example, for you guys, if I take this piece of paper, which usually has a pretty high air resistance, right? And I take this IED kit, both of these would hit the ground at the same time, right? Okay, if there's no air resistance, right? So like if I drop this one, pretty much goes at the same rate. This one, a little slower, right? But what if I said I can get both of these to actually hit the ground at the same time? If you ignore air resistance, if you get rid of the air resistance, they fall and they hit the ground at the exact same time, the paper included. You can't really say, because I know the most common thing was whenever I talk about that, a lot of people are like, well, wait a minute. If I hold it like this and I put the piece of paper down here, they would say the kid up here is pushing this down. But you can't make that argument when the paper's on top, because what would actually be pushing it down? There's nothing there. Okay. This is the same kind of thing that happens whenever you try. Please don't do this, but the same thing kind of happens whenever you go behind an 18 wheeler. If you get too close to it, you actually feel there's like not that much wind behind it. Okay. My grandfather used to intentionally get behind 18 wheelers because it would give him better gas mileage. And he's like, it's better gas mileage back here. And you're like, that's kind of scary actually, because you're a little bit too close to one of those things. Okay? So we can use these kinematic equations, and that last one, this bottom one down here, this is golden for falling things. This is golden for falling things because you have all of the information that you need, and if you have got a stopwatch and you know that you're on Earth, you can find out how tall something is just by measuring it with the timer. Okay? So, and you time how long it takes something to fall. Now, I don't know if you guys actually just like time things that fall or not, but I don't know if you realize this, but things fall pretty quickly. Okay, so like think about something that falls for an entire second. How far does something go if it falls for an entire second? 9.8 meters because of the 9.8 meters per second squared. We can find out exactly what that is if we put in 1 right here. Okay, but think about this, okay? Think about this. I usually like to think about it in terms of scream times, okay? Because like if somebody falls, like if they're on a ladder and they fall off, they're like ah, and they fall, right? Okay. Imagine somebody screaming for 1 entire second. How long would that fall have to be for somebody to like ah? It's a long time, right? Yeah. Sure. Yeah. Yeah, that's true. Gravitational acceleration is the same no matter what. So Negative, Ghost Rider. The gravitational acceleration will be the exact same number every single time. As you continue to fall down, it will be 9.8 meters per second squared. When you are standing on top of the cliff, it is 9.8 meters per second squared. When you're taking a nap in the middle between lunchtime, which I totally don't do, it is 9.8 meters per second squared. If you are driving home, it is 9.8 meters per second squared. If you are on the planet Earth, the acceleration due to gravity is 9.8 meters per second squared. Yeah. Can we calculate that? We can use the kinematic equations and we can prove whether or not it will be 9.8 meters per second at the first second. So using this one, we can calculate what that speed is, and I do believe that that is correct. Let's try and let's verify because we don't have to pretend with the kinematic equations. I don't know if pretend's the right word. We don't have to guess or approximate. With the kinematic equations, we know without a shadow of a doubt. So if we use that top kinematic equation, I'm getting ready to use an expo marker for my screen. That's not a good idea. If we use Vf equals Vi plus At, we know that the final velocity is what we're looking for. We know that the initial velocity is 0 because we're dropping it. And then we also know that it's going to be falling for 1 second. The acceleration due to gravity is negative 9.8 meters per second squared. And the time is t. So, according to that first kinematic equation, we can say that Vf is equal to negative 9.8 times 1 second. So our velocity after we fall for 1 second is going to be negative 9.8 meters per second. True statement. Okay. Yes, and that velocity increase is linear. So if you are covering a half a second, in the first half a second, you'll be traveling at 4 point whatever meters per second. Okay. Now, for the distance that gets traveled, we can use the third kinematic equation, and that should work out for us as well, too. So if we use this third kinematic equation, the distance is going to be equal to 0, because that's VI would be 0, plus 1 half negative 9.8 times 1 second squared. And I better put my meters per second squared in here too, just to be unit efficient, because the second squared cancel out on the top and on the bottom down here. So it's just good proof that these kinematic equations are dimensionally valid, and the trauma that I put you guys through at the beginning of the year was for a reason. Okay, so as we do this, is this answer going to be 9.8? Oh, okay, so this is going to be negative 4.9 meters. No, not squared, sorry. It's going to be negative 4.9 meters after you do the 1 half and the 9.8. Okay, so a fall of 1 second, one whole second of falling is going to get you 5 meters of fall. So that's here, 2, 3 is to the ceiling, and then 2 more after that. So you're basically looking at a 2-story fall if you're falling for 1 second. Okay, it's not going to be pretty. And if you go up any higher than that, it just gets worse from there. So if you are dealing with 1 second or greater falls, it better not be you that's doing the falling. Okay, there better be something else there that's falling besides you, or that's not going to be good for you. Okie dokie. You are welcome. Squirrels can totally do that. Yeah, squirrels can fall like out of trees instantly, and they just like, "Wah," and they just hit the ground, and they just get up and go. But that's because whenever their little fluffy bodies are so light that the air resistance pulls them back, and they don't fall nearly as fast as we do. You should because they're everywhere. Okay. Yeah. Yeah. Not fun. Yeah, not fun. I would definitely say any kind of fall where you're having like anything above like 1 or 2 meters, not fun at all. Um, but we can use these kinematic equations to solve for pretty much like any word problem. How much time do I have left before I keep going? We get out at 10:48. Oh, okay. So we got like 4 minutes left. Let me write down like the basic procedure that I normally do. So like let's just pretend that this is a word problem. Word problem, 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 9.8, meters per second squared, 4.2 meters. So when you see a word problem, scan for numbers automatically because those numbers are going to mean something to us. Sometimes they're implied inside the problem. So like if you're dropping something, that's implied that the initial velocity is 0, but they're not going to tell you flat out that the initial velocity is 0. But scan for those numbers and look for things like the displacement, the initial velocity, the final velocity, the acceleration, and the time. So notice I wrote out dvat, but I made it a little bit extra. So it's like diva, but it's like dvat. I don't know. I'm just trying to think of ways to try to remember this stuff. You should, if you work one of these problems out, you should have enough to squeeze in everything into one of the equations except for one variable. Usually acceleration is given to you. So I'm going to go ahead and write here that the acceleration is usually negative 9.8 meters per second squared. Um, I need to write usually because that's not always the case. If you're falling, it is always assumed negative 9.8. Obviously, if you're in a car and that car is accelerating and you have to find the acceleration of that car, you can't just plug in 9.8 and be like, oh, it's on Earth, because that's not what it's asking you for. It's asking for whether the car's sped up or slowed down, not how it's being pulled down by gravity. But if you don't see it in the problem itself and it's falling, you just assume that it's negative 9.8, or you can use negative 10 and get away with it. Okay? But I think I'm going to stop there, and we'll try some either kinematic graphs tomorrow or these kinematic equations. I don't want to go too fast, but at the same time, we have things to do.